Stoichiometry. Old name for unit conversion math. I believe it's German derived. But what are we going to talk about today? We're going to talk about converting a weight of one compound, so a mass of A, into mass of B. So what does that mean? If I've got a balanced reaction, let's go back to methane plus O2 goes to CO2 and water. So I've got, let's say we have one methane, gives me one carbon, so I need one carbon dioxide to keep the carbons the same on both sides. This gave me 4 hydrogens, so I'm going to need 2 waters to get 4 hydrogens. This gives me 2 times 1 and 1 times 2. It gives me 4 total oxygens over on the right. So I need 2 dioxygens. I have 4 total oxygens on the left. Balanced reactions, part of why we need them is so that we can figure out how much of things we need. When you have a power plant and it's burning natural gas to make power, which is one of the most common power plants right now, the boom in fracking in the US has created an enormous amount of methane gas availability. So most modern new hydrocarbon power plants burn methane. It burns fairly clean, but it still makes a lot of CO2. It's not solar or wind or things like that. How much carbon dioxide are you going to produce? As we debate things like carbon taxes or trying to figure out how to limit carbon emissions, we need to know how much we're making. And so to do this, if you were told you had 20 grams of CH4 as you're starting, and you burn it, our goal is to find grams CO2 formed. Now granted, a power plant is going to be burning tons an hour, but the process is the same. I have a weight of the chemical I put in. I want to know the weight of the chemical I get out. To do this, well, you cannot compare 2 molecules in weight. If I have, if I say I have 1 brick of lead and I have 1 feather, I have 1 of each, but one's heavier, right? And if I say, okay, I have a pound of both, well, a pound of lead is a small cube, but a pound of feathers is half my pillow. Right? In terms of size and volume and number, they're quite different. Balanced reactions are numbers. They are the number of atoms, the number of molecules. We must compare molecules by number, which in chemistry is the mole. So we need to use moles. Our first step here, if I want to go from weight of one thing to weight of something else, is I need to find those moles. So how do we do that? Well, molecular mass, if you think back, we added up the individual elements. Carbon on the periodic table is listed as 12.01 grams per mole. Hydrogen is listed as 1.01, or close enough depending on your periodic table. Except I have 4 hydrogens. I need to add these up because I need to convert that weight of methane into number of methane. And so 12 plus 1 plus 1 plus 1 plus 1, 16.05 grams in 1 mole for methane, for CH4. This was a molecular mass. This is critical to doing our question above. The idea is I have 20.0 grams of CH4. My end goal is to find grams of carbon dioxide, but I can only compare them if I'm in number, if I'm in moles. So I need to get out of grams of CH4 and into mole of CH4. Molecular formulas, they act like variables. Units, they act like variables. If you had x times x over y, well, the x's would cancel out. This would be x times y over 1x. My x's would cancel. Your answer is just y. Right? You can get rid of those grams and turn it into moles. You can say, how many moles of this chemical do I have? And we need to do it in moles because that's the number unit for chemistry. Doing it in actual atoms is phenomenally huge. 6.022 times 10 to the 23 molecules per mole. The number becomes too unwieldy very quickly, so we do it in moles. I can take my starting weight of methane and I can turn it into number of methane. I say, well, it's 16.05 grams of methane in every 1 mole. This is where the molecular mass comes in. This is why we need it. Every chemical that you'll ever have a weight for, you need to find the molecular mass to turn it into moles of that chemical. And we always need to find the moles if we're ever comparing it to any other molecule. So I'll give you a rule right now. If you're not certain what to do, the very first step is always to find moles. Even if you think you know what you're supposed to do, probably the first step is to find moles. Right now we're doing it using weight and molecular mass. Later with solutions we'll use volumes and concentrations and other means, but you're almost always trying to find moles so that you can compare compounds. So if we add this up, we will find 1.246 mole of CH4. If you think about it for a second, I had 20 grams, and it only took 16 grams for a mole. So I've got a bit more weight, and I find I have a bit more than 1 mole. My grams of CH4 canceled with grams of CH4. 20 times 1 divided by 16 came out 1.246. I was still in moles of CH4, which is the unit we see. What I've done is I found the number of methane. What can we use that number for? We'll go back up above. We know that for every 1 methane, I must make 1 CO2. You can't change those coefficients. You need 2 tires on a bike or it really doesn't work. Same with the balanced reaction here. Like they're set. For 1 methane, I must produce 1 CO2. If that methane reacted, it made 1 CO2. This allows us to convert between molecules. I know that 1.246 mole of CH4 was around. I can get out of mole of CH4, the number of them, and into the number, the moles, of CO2. For that, I need the balanced reaction. What is the coefficient of methane? It's 1. What is the coefficient for CO2? It's 1. Granted, timesing by 1 and dividing by 1 won't give us a different value, but that's just because they're the same number. 1.246 mole of CO2 is produced. When those 20 grams of methane are burned, well, they represented 1.246 moles of methane. They will produce that exact same number of CO2s. Unit-wise, my mole of CH4 is on top and on bottom, so they cancel. I'm left in mole of CO2. The final step then was we wanted to find the grams of CO2. Most of those carbon taxes are by weight. And so we sit there and need to convert my moles of CO2. Well, I want it to be grams. My end answer wants to be grams of CO2. What I need is to get rid of the moles of CO2 and get it into grams of CO2. I need some values. But if I had a ratio, my moles would be on top and bottom and they could cancel out. And I'd be into grams of CO2. So where can we get a gram to mole ratio of carbon dioxide? Well, it goes back to molecular mass. CO2, carbon is 12.01. Oxygen is 16.00, except we have 2 of them. So this adds up to 44.01 grams per mole. Grams are on top. There is 44.01 grams for every 1 mole of carbon dioxide. So my moles times 44.01, 54.84 grams of carbon dioxide. We put in 20 grams of methane, which was a certain number of methane molecules. We obtained the exact same number of carbon dioxide molecules, but those, because they are heavier, the total weight of those carbon dioxides is actually 54 grams. So we've been able to determine, based on what we burned, how much CO2 weight we produced. In terms of significant figures, well, I started with 3 sig figs. My molecular masses all had 4 from adding them up. So my values would still have 3. I'm multiplying, dividing, so I use whatever I have the least. Coefficients are perfect. This isn't a 1 sig fig answer. You need precisely 1 methane for every 1 carbon dioxide. So there's no change in sig figs. It was 3. It is still 3. It is still 3 going into our last calculation. Our added up molecular mass was 4. And so our final answer is going to have 3 sig figs for a final answer of 54.8 grams of CO2. Now, this is how you take a weight of one chemical and convert it into weight of another chemical. There's a short outline, but the first step, if I want to go from grams of A to grams of B, is I must take the grams of A, use the molecular mass of A, put the grams of A in 1 mole of A. The next step is the balanced reaction to say moles of A to moles of B. And the third step is a molecular mass of B with the moles of B on bottom and the grams of B on top. This will allow us to convert to grams of B. This is true for jumping between any 2 compounds in a balanced reaction. They don't have to be starting material and product. They can be product to product, starting material to starting material, product to starting material, or any other mix between.